All right, welcome to the after work video. We learned about the multi-layer perceptron in the last video, the most basic form of an artificial neural network. So moving on. In a neural network, all the perceptrons will work coordinately to produce a specific result. The input X is propagated forward through the different layers, and the output of one layer serves as the input to another layer. Eventually, this produces the final result in the output layer. The result will have a certain error characterized by the loss or cost function. Gradient descent is the mechanism we use to minimize the cost function of the entire model and iteratively obtain the weights for each perceptron that provide the optimal result. However, one key question is, how do we run the gradient descent in this context, as it requires computing the derivative of the cost function by all the different weights. Quite complex. Fortunately, there is a mathematical trick which I will not elaborate in detail because it is a bit convoluted. The trick is called backpropagation. The intuition behind it is the following. For every layer, the error produced in the output can be proportionally decomposed for each of the input signals for the perceptrons in such a layer. Essentially, we can decompose the error function in each layer as a function of the error introduced by the previous layer. Hence, we break a big derivative calculation into smaller derivatives that can be combined. In some sense, we are backpropagating the error from the output to the input. In that process, we are computing by how much each of the weights needs to be updated to execute the gradient descent algorithm. This mathematical trick enables us to train arbitrarily complex or large neural networks as long as we can compute the derivative of the different cost functions. Already available Python libraries usually handle this. In general, unless we want to implement something really specific for a use case, we will simply use standard cost functions and activation functions for which derivatives can be automatically computed. This magic happens under the hoods. Several hyperparameters will determine how the training process is executed, and as a consequence, its success or failure. As always, brute force will be your friend, and you may need to try different options to find what works best for your use case. As already referred, it is a bit of an art of intuition, experience, and a lot of try and error. He means trial and error, leveraging as much compute, memory, and storage you may have available. GPUs will definitely be your friends. Some of the key hyperparameters to choose are: how many layers should I use? How many perceptrons per layer? If you choose to have more than one hidden layer, therefore your neural network has 3 or more layers, considering the inputs is not really a layer per se, but we count it as one. Congratulations and welcome to the world of deep learning. A deep neural network is simply a neural network with more than 3 layers, or effectively 2 or more hidden layers. It is as simple as that. When you hear about deep learning, it is really about using basically large and deep neural networks. We will do a quick review of a few types of them, but essentially it is about building large neural networks. As you can imagine, because those networks will be large, they are very complex in the model complexity definition we discussed in the overfitting section. Therefore, this type of approach is only valid when you really have a very complex reality to model or predict and many millions observations in your data set. So, if you are curious about deep learning, it is simply using neural networks with more than 3 layers. The neural networks we have seen so far are referred to as feed-forward or dense neutral networks. Essentially, they are fully connected, dense, and the signal is fed forward from the input layer to the output across the multiple layers. It moves unidirectionally. So, quite a sophisticated drawing there. This is a deep forward feed neural network. I'm not sure what is meant by forward feed. So let's get a so let's feed it to ChatGPT.
The diagram you provided illustrates a deep feed-forward neural network, which is a type of artificial neural network designed for supervised learning. Here's a breakdown of its architecture and functionality. Architecture. Input layer. This layer consists of input neurons that receive various forms of raw data, e.g., pixel values for images, feature values for tabular data. The number of neurons in this layer corresponds to the dimensionality of the input data, x1, x2, xmx_1, x_2, ldos, x_mx1, x2, xm. Hidden layers. The network includes multiple hidden layers, each composed of neurons denoted by P in the diagram. These layers are called hidden because they are not directly exposed to the input or output. Each neuron in these layers applies a weighted sum to its inputs and then passes the result through a nonlinear activation function, not shown in the diagram but typically employed in practice. The presence of multiple hidden layers, more than one, makes this network a deep neural network. These layers enable the network to learn complex patterns through progressively abstracting the inputs. Output layer, the final layer in a neural network structure, where the outputs are computed based on the transformed inputs through the network. The output could be a single neuron for binary classification tasks or multiple neurons for multi-class classification or regression tasks. Functionality, feed forward. In this type of network, information moves in only one direction, forward, from the input nodes through the hidden nodes, if any, and to the output nodes. There are no cycles or loops in the network. This architecture is why it's called feed forward. Depth. The depth of deep learning refers to the number of layers through which data is transformed. In deep networks, as the number of layers increases, the network's ability to recognize and represent more complex features and patterns also increases. Learning process. Weight adjustment. Through training, the network adjusts the weights of the connections between neurons across all layers to minimize the prediction error. The most common training algorithm used is backpropagation combined with an optimization technique like stochastic gradient descent, SGD. Loss function. During training, the loss function evaluates the network's performance by measuring the difference between the predicted output and the actual output. The network learns by iteratively minimizing this loss. Applications. Image recognition. Deep feed-forward networks are foundational in image processing tasks, where they can identify and classify objects within images with high accuracy. Speech recognition. These networks are used to recognize spoken language and convert it to text. Financial forecasting. In finance, they predict future financial events based on historical data. Deep feed-forward neural networks are a cornerstone of modern AI and are fundamental to many complex problem-solving tasks across various industries and sectors. Their ability to model and make predictions based on large and complex data sets is unmatched, making them indispensable tools in the arsenal of data scientists and machine learning engineers.
All right, sounds good to me. How many layers should you use? How many nodes on each layer? These are all decisions you will need to make, along with a few other hyperparameters. As an intuition, adding more layers usually has a better impact when your model needs to capture better your data complexities than adding more nodes to the existing layers. However, this generalization may not be accurate depending on the case. As referred, try and error and experience will guide you if you want to play with these technologies. But at the minimum, it is essential that you understand for deep neural networks to be used, you need to have a very complex problem with a very, very large volume of data available. Not in the order of thousands of observations, but in the order of millions, preferably. Typical use cases are image processing, text processing, audio. If your use case fits in a different type, deep neural networks are likely not necessary nor convenient, may not even be neural networks, maybe not even neural networks at all. The ability of these models to learn is immense. Millions or hundreds of millions or even billions of parameters to learn. You must therefore understand that overfitting can happen very quickly. There is no free lunch. Training such complex models is expensive in time and compute resources. State-of-the-art language models can take 1 month to train and cost millions of dollars in cloud computing resources. This is not a game at the reach of many organizations, nor is it likely that the problem we plan to solve needs such a game. We will see some use cases in the practical section where we use deep learning with somewhat small models. Still, it takes a good number of hours to train, and that's fine. Okay, so key takeaway. A neural network is a large non-linear system whose expected behavior is highly unknown a priori. So before it's run, you're not sure exactly how it's going to, what the results are going to be. They are very powerful, but their effectiveness can only be evaluated by trial and error. Okay, and we saw that neural networks is just one type of machine learning technology. So neural networks, yes, they scale up fast. The more difficult the task, the more state of the art you get with neural networks, the more you have to pay. There's no way around that. But not everything needs a neural network, and there are some things that don't require state-of-the-art neural networks. All right, so moving on, controlling the power of your neural network. And I'll advance the bookmark. Overfitting is a likely scenario with a neural network, particularly with one that has multiple layers. Earlier in the book, we introduced the concept of regularization. Regularization tries to reduce the complexity of the model so that it focuses more on learning the pattern and less on noise. As you can imagine, the complexity of a neural network is highly associated with the number of layers and nodes per layer. This results in the total number of weights that the model needs to learn in the training process. But what if we disable some of those nodes during the training process? Like if we shut them down, not permanently, but only during some short periods and in a random way. Somehow we are making the model to be less powerful because the number of nodes that can learn is slower. However, we are randomly picking those nodes such that the model cannot rely anymore on any specific node to make decisions, because that node may, at any point in time, be disabled. It somehow forces it to find other ways to detect patterns. We are effectively making the neural network struggle a bit during the training process, making it more difficult. The expectation is that at inference time, when all the nodes are available, it will be better at detecting the patterns. This is very much analogous to the example I mentioned about forcing a tennis player to train with one hand tied to the back. It will be stronger in the actual game when it has both hands available. All right, so now we've got another one. This is a dropout in a neural network. So let's feed this to a neural network. And remember, this is the technique.
The image you provided illustrates a neural network that incorporates a technique known as dropout.
Right.
Dropout is a regularization method used to prevent overfitting in neural networks.
Yeah.
Here's a breakdown of the concept and its application in the network. Dropout concept. Purpose. Dropout is designed to improve the robustness of a neural network by randomly dropping out, i.e., temporarily removing during training, a subset of neurons in the network layers. Random deactivation. During training, each neuron has a probability of PPP of being temporarily dropped from the network. This means it is temporarily ignored during a forward and backward pass. The probability of PPP is typically set between 0.2 and 0.5. Effect on training. By dropping out different sets of neurons, it ensures that no single neuron can rely on the presence of particular other neurons. It forces the network to learn more robust features that are useful in conjunction with many different random subsets of the other neurons. Functionality in the diagram. Network structure. The diagram shows a deep feed-forward network with several hidden layers. The neurons marked with a dotted outline are those that are dropped out during a training iteration. Input and output layers. The input layer receives the feature data x1, x2, xmx_1, x_2, ldos, x_mx1, x2, xm, and the output layer produces the result yyy, similar to standard neural network operations. How dropout works in training. Random deactivation. During each training pass, each neuron, except those in the output layer, has a chance PPP of being dropped, meaning it does not contribute to forwarding propagation and its weight does not get updated during backpropagation. Batch and epoch. This process happens differently for each batch of data during each epoch, meaning the network looks slightly different each time, increasing generalization. Model averaging effect. At inference time, when making predictions, all neurons are used, but their outputs are scaled down by a factor equivalent to the dropout rate to balance the fact that more neurons are active than during training. Benefits of dropout. Prevents overfitting. By randomly deactivating neurons, dropout prevents the network from fitting too closely to the training data, which can improve performance on unseen data. Generalization. Model robustness. It encourages the network to develop redundant representations to ensure some are likely still active despite the dropout, enhancing the network's fault tolerance and robustness. Applications. Large networks. Dropout is particularly useful in very large networks that would otherwise overfit easily. It is widely used in networks dealing with high-dimensional data like images and text. The dropout technique has been one of the key developments in neural network training, allowing for training deeper and more complex networks without a commensurate increase in overfitting risks.
Alright, so that looks good. This technique, called dropout, is very frequently used when training a neural network to somehow limit its complexity at training time. It forces the model to learn the patterns better and perform better at inference time. What percentage of nodes are disabled at any time is a configuration hyperparameter to choose. Key takeaway: dropout-based regularization is a way to control the model complexity and minimize overfitting. We have described the basic form of a neural network that we refer to as feed-forward or dense. However, while this architecture is theoretically capable of learning any pattern and non-linearity, it may not be taking advantage of certain information and specificities of the data that could be beneficial. For example, images are not usually presented as a vector. They are coded in the form of a matrix. There is a sense of sequence for certain types of data, like text or time series, where one data point may have specific dependencies from the previous or subsequent ones. This is all useful information that could help us build use case tailored architectures that can more effectively extract information and patterns from such data types. Note that you could still theoretically train a feed-forward network to deal with images or text sequences. However, the training may eventually take too long or simply not converge because it is too difficult for that architecture to do it. Let's review some of those frequent architectures. So the first architecture is convolutional neural networks. A convolutional neural network, CNN, is a particular type of architecture designed to deal with images. More precisely, it is intended to take advantage of the following. In images, the value of one pixel is highly related to the values of the surrounding pixels. In images, a specific shape or pattern may need to be detected irrespective of what position it has on the image, so processing should consider that. CNNs can be used not only for images, 2D matrix, but for sequences, 1D matrix, or videos, 3D matrix, or potentially n-dimensional matrices. Their benefit is to capture patterns among neighbor points and the ability to capture those patterns independently of where they happen in the matrix. Let's review how it is possible. The fundamental new ingredient is the convolution. Without going into the mathematics background, a convolution can be defined as a moving multiplication in layman's terms. In the context of the CNN, the convolution uses NXN filter that will be applied through the original image. The result of applying the filter, also known as kernel, to each NXN portion of the original image is a number, sum of the multiplication of the values on the original matrix by the filter values. This generates a new matrix resulting from the convolution of the original matrix with the selected filter. The filter is shifted through the image by certain positions, stride. As you can see in the diagram, the resulting matrix is not the same size as the original one. If we need the resulting image to have the same size, we may need to do some outer padding of the original one. All right.
The image you provided is a great visual representation of the convolution operation used in image processing and, more specifically, in convolutional neural networks, CNNs. Here's an explanation of the diagram and the process it illustrates. Components. Original image. This is represented as a three-dimensional matrix. In the context of CNNs, this matrix usually represents the pixel values of an image. The dimensions correspond to the height, width, and depth, color channels of the image. In your diagram, each cell within the matrix represents a pixel value. 3x3 filter, kernel. This small matrix slides over the original image matrix. The filter is used to extract specific features from the image, such as edges, corners, or other textures. The size of the filter, 3x3 in this case, is a design choice that affects how broadly features are sampled from the original image. Matrix after convolution. This is the output matrix resulting from the convolution process. Each element in this matrix is calculated by applying the filter to the original image, a process detailed below. Convolution operation. Sliding the filter. The 3x3 filter slides over the original image matrix. At each position, it covers a 3x3 block of pixels. Element-wise multiplication. The filter is multiplied element-wise with the pixels it covers. Summation. The results of the element-wise multiplication are summed up to produce a single value. This value becomes a single element in the resulting matrix. Bias and activation. Often, a bias is added to the sum before it is passed through a nonlinear activation function, like ReLU. This step is not explicitly shown in your diagram, but is commonly part of convolution operations in neural networks. Output matrix characteristics. Size. The size of the output matrix is determined by several factors, including the size of the original image, the size of the filter, the stride, how far the filter moves each time, and the padding, added pixels around the edge of the image to allow complete application of the filter. Commonly, if no padding is used and the stride is 1, the output matrix will have dimensions that are slightly smaller than the original image. Depth. The depth of the output matrix corresponds to the number of filters used during the convolution. Each filter generates a different feature map, capturing different aspects of the input image. Applications. Feature learning. Each filter can learn to detect different features from the input image during training of a neural network. This makes CNNs extremely powerful for tasks like image and video recognition, image classification, and medical image analysis. Automated feature engineering. Unlike traditional algorithms that require handcrafted features, CNNs can automatically learn the features directly from the image data, which greatly improves the learning capability and accuracy of the models. This diagram succinctly captures the essence of the convolution operation, a cornerstone technique in modern image processing and deep learning architectures.
Alright, so moving on. In the example above, the filter contains certain ones and zeros. This is only an example. In a CNN, the values of the filters are precisely the weights W we want the CNN to compute. In other words, those filters are not statically defined. They will be dynamically computed as the CNN is trained. The size and number of the filters are also choices. 3x3, 5x5, 7x7, and so on. You are likely noticing that the number of options is considerable, and as with most hyperparameters, the specific result is mostly unknown before you try. For that reason, there are CNN architectures, convolutional neural network architectures, that have already been predefined and somewhat tested, which you can simply leverage. We will discuss leveraging existing architectures and/or models in more detail. The entry point of the CNN is the matrix corresponding to an image. After the convolutions are applied, it becomes a feature map. Each value in that feature map represents a specific abstracted feature that the CNN detects. The intuition is that the initial layers of the CNN will detect basic features such as corners, vertical or horizontal lines, etc. The deeper the image traverses the CNN, the feature maps capture the more complex abstractions from within the image. As the data transverses the CNN, the size of the feature map changes. So there's the original image, and now we have convolution, pooling, convolution again, pooling, and then dense. So let's see what ChatGPT has to say about that. Usually has something good to say.
The image you uploaded provides a succinct overview of a typical convolutional neural network CNN architecture. This type of architecture is commonly used for processing structured grid data such as images. Here's a breakdown of each step shown in the diagram and the role it plays in the CNN. 1. Original image. Input. The process starts with the original image, formatted as a matrix of pixel values. This matrix can have multiple layers or channels, depending on the color depth, e.g., grayscale, RGB. 2. Convolution layers. Feature extraction. Each convolution layer applies numerous filters to the input. These filters are designed to detect specific features such as edges, colors, or textures. The output of each convolution operation is a feature map, which highlights areas of the image that activate the filter most strongly. Learnable parameters. The filters are represented by learnable weights that are updated during training to optimize the network performance on training data. 3. Pooling layers. Dimensionality reduction. Following convolution, pooling layers reduce the spatial dimensions, height and width of the input volume for the next convolution layer. This is achieved by summarizing the presence of features in patches of the feature map. Types of pooling. Common pooling operations include max pooling, taking the maximum value from a set of values, and average pooling, taking the average of a set of values. Pooling helps make the detection of features invariant to scale and orientation changes. 4. Additional convolution and pooling layers. Deep feature hierarchies. Additional convolution and pooling layers can be added to learn more complex patterns. Each layer effectively builds a more refined understanding of the input based on the features detected by previous layers. 5. Dense layer. Classification output. After one or more convolution and pooling layers, the architecture typically ends with one or more dense, fully connected layers. These layers compile the features extracted by the convolutions into predictions for the task at hand, such as classifying the image into categories. Decision making. The final dense layer often uses a softmax activation function and classification tasks to distribute the voting power of the network across the predefined classes based on the learned features. End-to-end process. Feed-forward network. This is a feed-forward architecture where inputs move forward through convolutions, activations, pooling, and finally through fully connected layers to produce an output. Backpropagation. During training, the network uses backpropagation to update weights and minimize the loss function, improving the accuracy of predictions against known labels. Applications. Image recognition. Used to classify images into categories, such as identifying animals and photos. Object detection. Locating objects within an image and classifying them. Automated image moderation. Detecting inappropriate content in uploaded images. This diagram effectively encapsulates a common pipeline in deep learning for image processing, highlighting the step-by-step processing of data from raw images to an interpretable output.
Okay. Alright, so moving on. So the overall process that we progressively reduce the size of the feature map to a smaller but more abstract set of inputs. The size of the layers is reduced, height and width, by both the convolution filters and some layers focused explicitly on summarizing. Those are referred to as pooling. A pooling layer will reduce the size of the feature map by 2 by simply selecting the max value of each 4 neighbor cells. That is called max pooling. Ultimately, the goal is to reduce the size and progressively get to a D1 vector that becomes the input of a feed-forward dense neural network at the end, typically 1 or 2 layers. This is where the final classification or regression happens and produces the expected output. It is important to remember that every neural network's mission is to resolve a non-linear problem. I have explained the convolution operation and the pooling, but both are linear. While I have not highlighted in the diagrams for readability after every convolution, there is an activation function that will provide the nonlinear behavior at every layer. Most of the time, the function used is RELU or leaky RELU. So we remember those functions from before. Those are the ones that will be used most of the time to provide nonlinear behavior at every layer. So you can have between your layers, you can have sophisticated things happen between the layers depending on the sort of functions that you use. All CNN architectures will have several convolution and pooling layers, mainly potentially, or many potentially. So like a lot, maybe millions, billions. I don't know what he means by many. And we'll end with a set of dense layers. Or it could end with a single dense layer. When we look at the number of weights to be learned, the vast majority belong to this final dense layer. The convolution layers are responsible for progressively selecting the features from the image/input matrix relevant to the task at hand, classification or regression. It is really the final dense layer where most of the decision happens based on the highly abstracted features that the convolutional layers have produced. Earlier in the book, I mentioned that there would be a feature selection process as part of a machine learning project. In this process, out of the input data, we pick manually the variables we are interested in, or maybe we create new ones if we think they will be relevant to the problem, derivative, rate, difference, and so on. However, what we see here with the CNN is that somehow it is magically figuring out what the key features on the image are. The CNN automatically calculates the filter weights that will be the most effective for the classification or regression task, which the dense layers will perform at the end. This is exactly what is happening. It sounds magic, and sometimes it is complicated to comprehend. That is one big problem of any neural network, the poor explainability of what is going on. But the CNN figures out by itself the features that matter from the image. Given the flexibility of this approach, lots of different possible combinations are possible. Over the years, research teams have designed specific combinations that provide particular benefits, both through experimentation and deep research on the dynamics of the training process. Subsequent architectures have solved the limitations and issues of the previous ones. Examples of those architectures are AlexNet. This was a real revolution back in 2012 and the start of the era of deep learning. VGG, GoogleNet, Inception v1. ResNet enabled very deep architectures, more than 1,000 layers. DenseNet, etc. I will not describe them. You can find literature and papers, but the most important part to highlight is that the research community has produced public architectures, which can be leveraged as is, or with modifications if required. Those architectures have proven to be very effective in image detection use cases. They can be applied to other image-related use cases and even non-image related. How are CNNs relevant for you as a network engineer? There are use cases where a CNN would be used to process network data. Remember that CNNs can process sequences as well as matrix representations of data. We can frequently find such representations in networks and clouds. Okay, so recurrent neural networks is the next one. Let me check the clock. Oh, only 35. Well, man. I think I want to stop here. I'm coupling this. I'm habit stacking, so I'm doing exercise as well, and I just feel like I need a break. I guess I could just stop exercising and sit down. Maybe that would help. Yeah, I have a treadmill. I have resistance bands. I have grip strengthening gear, and I'm doing that and reading this book, and it's become a bit much. So, okay, I'm just sitting down now, so I actually do feel a lot better, and I'm going to continue. Okay, so recurrent neural networks, RNN, and their derivatives, GRU and LSTM, are a type of neural network architecture optimized to work with data that is presented as a sequence. Usually, it is a time sequence, but it can be any sequence. Examples such as time series metrics, text, voice, music, or audio. RNN, which we remember stands for recurrent neural network, leverages that in sequences. The value at a particular time is strongly related to the previous values or even to the values after. Therefore, it makes sense to enable mechanisms to connect one value to its previous values. You could also think that a CNN, which is a convolutional neural network, has that property, and it is true. Sometimes CNNs, convolutional neural networks, can be used instead of a recurrent neural network, RNN, as CNNs can deal with 1D vectors that could be interpreted a sequence. However, recurrent neural networks, RNNs, take advantage of this property of sequences in a different way by having memory. The output in the hidden layer is fed back to it so that the previous hidden state influences the output of the current state. If we unroll the RNN and visualize it over time, we get a structure as in the diagram below. Alright, so take a look at that.
The diagram you provided showcases the transformation of a neural network architecture from a single layer or simple network representation on the left to a more complex, multi-step, possibly recurrent, neural network on the right. Here's a detailed explanation of each component in the overall process. Left diagram, simple neural network, input layer, X. This layer consists of input neurons that take in the data to be processed. In the simple representation, it feeds directly into the next layer without explicitly showing multiple steps or sequences. Hidden layer. This is typically where computations are performed on the input data. Neurons in this layer apply weights to the inputs, and the results are passed through an activation function to introduce nonlinearity. Output layer, Y_T. The output layer receives the processed data from the hidden layer and transforms it into the final output of the network. This can be a prediction, classification, or any other type of output the network is designed to produce. Right diagram, unfolded network for sequential data. Input sequence, X_0, X_1, X_2, X_3. Here, the inputs are shown as a sequence, typical in context where the input consists of temporal or ordered data. Each XT_text represents an input at a specific time step. Processing nodes. Each node in the sequence likely represents a processing unit, such as a neuron or a group of neurons, that handles data from the corresponding time step. This is typical of recurrent neural networks, RNNs, where each step involves processing an element of a sequence, incorporating the previous step's information. Output sequence, Y_0, Y_1, Y_2, Y_3. The network produces an output at each step, corresponding to the input at that step. This is typical in tasks like sequence prediction, time series analysis, or any scenario where outputs are required for each input instance in the sequence. Transformation and functionality. From single output to sequence processing, the transformation from the left to the right diagram illustrates how a network handling a single input-output pair can be adapted or visualized to handle sequences where each input is processed over time or steps. Recurrent neural network, RNN. The right diagram strongly suggests the architecture of an RNN, where outputs from one step and feedback as inputs to the next, allowing the network to maintain a form of memory across inputs. Each box in the hidden layer sequence could be an RNN cell, processing both the current input xtx_text and the output from the previous cell. Applications. Such architectures are widely used in speech recognition, natural language processing, e.g., translation, sentiment analysis, and other applications where data points are interdependent and ordered. This diagram efficiently captures the essence of processing sequences in neural networks, highlighting how networks can be adapted or visualized to handle complex data structures beyond simple, one-off inputs and outputs.
All right, so that looks good to me. So moving on, this method forces the architecture to use the past as an input. When we are in t=1, we will feed an additional input, the results of the processing at t=0. This incentivizes the neural network to learn the context from the previous observation. All right. Recurrent neural networks may be unidirectional or bidirectional, so we can force the model to learn context both from the past and from the future. You may think, how do you learn from the future if it has not happened yet? When you train the neural network, you have a specific set of sequences. If you want, for example, to use the recurrent neural network, the RNN, to translate a sentence from English to Spanish, the first word in the Spanish sentence may depend on the second, third, or fourth word in the English one. So it is possible to set those conditions so that the model can build those relationships. Yeah, so languages sometimes have things out of order. So instead of can I go to the store, go to store can I, that's a common difference between languages, is like the ordering of the grammar. At inference time, it means it will have to wait for the whole sentence to be ingested to produce the first word out. One shortcoming of the RNN architecture is that it has difficulties in learning state from the long-term past. While the output of the hidden layer influences the next step, and some of it may also be passed to the subsequent steps, it has difficulties extending it beyond a small number of steps. That triggered the enhancement on the RNN into what it is called long short-term memory, LSTM neural networks. And I think this is a typo here, but the meaning's preserved. So RNNs became enhanced by So RNNs have a major shortcoming. So the shortcoming is, it has difficulties in learning state from the long-term past. So it was enhanced, it was rewritten, and it was turned into long short-term memory, LSTM neural networks instead. So RNN probably isn't used that much today, I would assume. But who knows? All right, so let's see what ChatGPT has to say about this.
The diagram you provided illustrates the basic structure of a recurrent neural network, RNN, cell using the hyperbolic tangent, tanh activation function. Here's how the RNN operates and the significance of its components. Components of the RNN cell. RNN cell. This is the basic unit of a recurrent neural network. The cell takes an input at each time step and produces an output while maintaining a hidden state that captures information from all previously seen inputs. tanh activation function. Inside the RNN cell, the tanh hyperbolic tangent function is used as the activation function. This function outputs values between -1 and 1 and is effective at capturing nonlinearities in the data. The trace of tanh helps in controlling the range of the output, which can mitigate issues like exploiting gradients in networks with long sequences. Inputs and outputs. Input. At each time step, the RNN cell receives two inputs, the current input from the sequence and the previous hidden state. Output. The cell outputs two things, the new hidden state and the output for the time step. The hidden state is passed back into the cell in the next time step, and the output is used for further processing or as the final output of the network. Functionality of the RNN cell. Feedback loop. The diagram shows arrows feeding back from the output of the cell into its input. This loop represents the recurrent nature of the RNN, where outputs from the network at one time step become part of the inputs of the next time step. This feedback mechanism allows the network to remember information across different parts of a sequence. Sequence processing. RNNs are particularly suited for tasks involving sequential data such as time series prediction, natural language processing, and sequence generation. Each cell processes one element of a sequence, with the output depending both on the current input and the information carried over from previous inputs. Challenges and considerations. Vanishing and exploding gradients. RNNs can suffer from vanishing and exploding gradients, especially with long sequences. This occurs due to the repeated multiplication of gradients through the network during backpropagation, which can cause gradients to shrink exponentially, vanish, or grow exponentially, explode. Memory of the network. While the recurrent structure allows the network to have a form of memory, this memory is typically short-term, and maintaining information over long sequences can be challenging without modifications like those introduced in long short-term memory, LSTM, networks or gated recurrent units, GRUs. The diagram effectively encapsulates the cyclical nature of RNNs, highlighting how information is recycled within the network to maintain a memory of previous inputs while processing sequences. This architecture makes RNNs uniquely capable of handling tasks where context from earlier in the sequence significantly influences the interpretation or processing of later elements.
Alright. So, LSTMs, which we remember are long short-term memory neural networks. So LSTMs are an improved version of RNN that can propagate state over a longer term, enabling the cells to be influenced both by the short-term past state or the long-term. Same applies to the future. Perfect.
The diagram you provided shows the internal structure of a long short-term memory, LSTM, cell, which is a type of recurrent neural network, RNN, architecture designed to address the vanishing gradient problem inherent in traditional RNNs. Here's a breakdown of its components and how it functions. Components of the LSTM cell. Input, XEX_text. This is the current input to the LSTM cell, typically part of a sequence being processed, like a time series or sentence. Previous in state, HT-1, H_T1, HT-1. This represents the output from the LSTM cell at the previous time step, which carries information from earlier in the sequence. Previous cell state, cord-1C_T1, cord-1. The cell state is a vector that travels along the entire chain of LSTM cells, carrying information throughout the process of the sequence. It acts as a memory of the cell. Gates. Forget gate, sigma, decides what information is discarded from the cell state. It looks at HT-1, H_T1, HT-1, and XEX_text and outputs a number between 0 and 1 for each number in the cell state cord-1C_T1, cord-1. Input gate, sigma, decides which values to update in the cell state. It also includes a 10H layer that creates a vector of new candidate values, C_TL, C_TC_T, that could be added to the state. Output gate, sigma, determines what the next in state HTH_THT should be. It considers the current input XEX_text, the previous in state HT-1, H_T1, HT-1, and the updated cell state CTC_TCD. Cell state update. The cell state CTC_TCD is updated by multiplying the old state cord-1C_T1, cord-1 by the forget gate's output, which forgets the things it decided to forget, and then adding the product of the input gate's output and the candidate values C_TL, C_TC_T, which updates it to new values. Output calculation, HTH_THT. The output HTH_THT is calculated based on the output gate's activation, which decides which parts of the cell state make it to the output, passed through a 10H function to scale the values to between -1 and 1. Functionality of the LSTM. Handling dependencies. LSTMs are capable of learning long-term dependencies because the cell state carries relevant information throughout the processing of the sequence, with gates regulating the flow of information. Gates operations. Each gate within the LSTM has a specific function. The forget gate decides what information is irrelevant and can be thrown away. The input gate decides what new information is stored in the cell state. The output gate decides what information from the cell state to output at this time step. Applications. LSTMs are widely used in sequence prediction problems, such as time series prediction, natural language processing, like machine translation, and speech recognition. Their ability to maintain and modify a cell state over time makes them particularly effective for tasks where the gap between the relevant information and the point where it is needed is large. The diagram effectively encapsulates the LSTM architecture, highlighting how it selectively updates its memory, cell state, and controls the flow of information, making it highly effective for tasks involving sequences with long-range temporal dependencies.
Alright, so moving on. The LSTM, which remember stands for long short-term memory, internal architecture, has a larger number of controls and a new path called the cell state, CT. The cell state is the feature in the LSTM that facilitates information propagation for more extended periods. As you can see, only linear operations happen from CT-1 to CT. I will not enter into the detail of all the components of the LSTM cell, but will only highlight the following. Number 1, it has the ability to control how much of the past state is propagated to the future and how much is replaced by the current state. Number 2, it, meaning the LSTM cell, so the long short-term memory cell, differentiates the output of the cell H from the cell state C, so they can be generated independently. And number 3, given it is more complex than a recurrent neural network, it has a larger number of weights to train. Long short-term LSTN. Oh, I said a typo? I think this might be a typo. There's an N here instead of an M. I think it's a typo. I think it's meant to say LSTM, long short-term memory. Neural networks are quite slow and complex to train, but provide very good results most of the time. So this is a typo. It's not worth going to the author to, though. I think I did report a typo to the author, which the author was awesome, and in like a few minutes responded to it, and he's going to correct it. But that was the typo of a mathematical operator that gave an impression that different mathematical operations were meant to occur than the ones that were. So this is not, I think, worth contacting the author for. It's just a small typo out of, all kinds of small typos and stuff. It doesn't significantly change the meaning like if it were a typo in a mathematical operator. In the practical examples section, we will see a few examples of log processing based on LSTM. There is a simplified version of LSTM called GRU, which requires less memory and is faster to train. Generally, it is important to note that any RNN has substantial memory requirements and is inherently slower to train than other architectures, such as feed-forward networks or CNNs, for a similar size or complexity level. Whether using plain RNN or LSTM, given that they work with sequences and each cell has 2 inputs, we can build different types of architectures depending on the type of input or output required. All right, so we've got many-to-many, and then we've got many-to-one and one-to-many. So let's see what the AI says about that.
The image you provided illustrates 4 common architectures of recurrent neural network (RNN) applications, specifically demonstrating how inputs and outputs are managed in sequence processing tasks. Each model is designed to handle different types of sequence-based data tasks, such as those found in natural language processing, time series analysis, and other areas where sequential data is prevalent. Here's a breakdown of each type. 1. Many-to-many, first diagram, use case. This model is typically used in tasks where both input and output sequences are of the same length. A common example is part-of-speech tagging, where each input word in a sentence is tagged with a corresponding part of speech. Operation. For each time step, there is both an input and an output, making this suitable for tasks requiring synchronous input-output mappings. 2. Many-to-many, second diagram, use case. This differs slightly in context from the first, often used in tasks like machine translation where the entire input sequence is processed before outputting the translation. The sequence lengths of inputs and outputs do not necessarily match. Operation. The entire input sequence is processed, and then the output sequence is generated, which may differ in length from the input. 3. Many-to-one USE case, common in classification tasks such as sentiment analysis, where a sequence of inputs, like a sentence or a series of sensor readings, is used to produce a single output, like a sentiment label. Operation. The sequence of inputs is processed through the network to generate a single output at the end. 4. One-to-many use case. This architecture is used in tasks where a single input generates a sequence of outputs. An example would be image captioning, where an image input produces a sequence of words as a caption. Operation. A single input is provided to the network, which then generates a sequence of outputs. Summary of architectural use. Many-to-many, used for synchronized sequence labeling or delayed sequence output like translation. Many-to-one, used when the entire sequence needs to be considered to produce a single output, common in classification. One-to-many, used when a single input generates a sequence, such as generating music or text from an initial seed. Each architecture variant is tailored to maximize efficiency and accuracy in handling specific types of sequential data, enabling nuanced processing suited to the unique demands of varied applications. The choice of architecture depends largely on the nature of the input and output data as well as the specific requirements of the task at hand.
All right, so there could be scenarios where, given a particular input sequence, the expectation is that we obtain an output sequence with the same number of elements. For example, we have a sequence of logs, and we want to get as an output for each log if it is anomalous or not, given the previous posterior logs. We will see an example later on this. This is a case of many-to-many, where the input and output sequence length is the same. Nevertheless, there could be cases where the input and output sequences do not have the same length. This happens with translation among different languages, where the length of the phrase in the original language may differ from the destination language. We can concatenate RNNs and have an output section where there is no external input X, but only the input from the previous RNN/LSTM. Somehow the output of that previous section has encoded the information contained in the input sequence. Next, with that encoded information, the last part of the neural network, the decoder, will build a new sequence to generate the output. All the information it has to work with is the hidden state from the encoder. This is a well-known architecture referred to as encoder-decoders. They are used in many scenarios because you can easily decouple the input format and length from the required output. You may hear or read the term seek to seek, SEQ to SEQ, to refer to these architectures as well, as they enable a transformation from an incoming sequence of a certain length to a new output sequence, potentially of a different length. Key takeaway: encoder-decoder or seek-to-seek architectures are very powerful and flexible solutions. They can address a large number of use cases where we need to transform an input sequence into a different output sequence with the same or different length. All right, so next session is autoencoders. This is where I have something else, so I need to stop this video. Now I notice I'm at 25%, which is kind of cool because that means I'm a fourth of the way done. Right. So it's pretty easy to predict at this point how long it'll take for me to complete this. So my first video was posted 13 days ago. So all we need to do is do 13 times 4. And I should complete the whole book in 52 days. So minus 13. So just another 39 days. So what will the date be 39 days from today?
Today is May 6, 2024. Adding 39 days.
So that's exciting. June by the end of June, so June 14th, I should be done with this series if I can maintain the same rate I've been going on. So yeah, that's exciting. That's the end of this video. Stay tuned for the next one on autoencoders.